going to see if I can cover 5 sections of the chapter 3, which is about stoichiometry, in order to, because, see how fast I can do it. I would consider all 5 of these chapters as sort of like the basics to math and chemistry, which is really called stoichiometry. They have a definition of stoichiometry in the book. I believe it's just the mathematics of chemistry. And a large part of that is fundamentally founded by the idea of counting by weighing. If you have a jar filled with jelly beans and you want to figure out how many jelly beans are in this this jar, well, one idea would be, all right, let me just take a bag of jelly beans, the same ones in that jar, and let me count out 100. Let me count out myself 100 jelly beans, weigh it, and I'll get a mass, and that tells me, oh, for 100 jelly beans, it's 50 grams, right? Now let me weigh the whole jar, and if I get a mass reading, well, I know what I can do is let's say the mass reading is 50, okay? In 100 jelly beans, there's 5. In a jar of jelly beans, there's 50 grams. Okay, 5 goes into 50 10 times. 50 divided by 5 is 10. So that means in the jar, because the count is proportional to the weight, right? The amount of jelly beans is proportional to the weight. Then if 5 goes into 50 10 times, well, this jar has 10 100 jelly beans. Oh, 10 times 100 is 1,000. It has 1,000 jelly beans, roughly. Each jelly bean is going to be a little bit different in weight, but that's a really good approximation. And the approximation gets better and better and better when your jelly bean gets smaller, less imperfections. Then it becomes super accurate. That's the idea of counting by weighing. And you're going to see that's pretty much the strategy we use throughout stoichiometry. If we know this fundamental ratio of jelly bean count to mass, right? Like 100 jelly beans is 5 grams. Well, then what you find is that 100 jelly beans is 5 grams. That's a really important ratio to know. That's going to help us forward. Atomic masses are going to sort of follow suit of that. So this is the atomic mass unit. Sometimes you'll see AMU. I write it as U. And 1 AMU is equal to the mass of, 12 AMU is defined as the mass of 1 carbon 12. So carbon has 12 atoms. So we decided, okay, let's just say 12 AMU is exactly 12 carbons. Hopefully you can kind of see what we're doing there. We're defining what is 12 AMU. We could have decided to say, let's just say 1 AMU is equal to the mass of 1 hydrogen, which typically just has 1 proton, right? We could have done it for oxygen. We could say oxygen, let's say 16 AMU is the mass of 1 oxygen 16. I guess carbon was just most abundant, and we just felt this is a good way to define carbon 12. Now the thing is, if you look at the periodic table, it tells you the atomic mass of every element, and there's usually decimals. And you'd think, well, based off this definition, carbon should have just 12 AMU. That should be the only element with just a 12.00000, but it's not. If you look at the periodic table, it's usually 12.01, because periodic tables take a weighted average of all the different carbon isotopes. Carbon 13 exists and carbon 14 exists. You could take a weighted average and be like, okay, if 93% of all carbon in the universe is carbon 12, let's say 5% is carbon 13 and then 2% is carbon 14, you can take a weighted average and be like, oh, well, on average, it's going to be 12.01 U. And by the way they figure out these atomic masses is through mass spectrometry. If you take electricity and magnetism in college, you'll kind of learn how it works, although I think they use a more sophisticated version of that to get more accurate results. So here's how to take a weighted average. If you don't know how to take a weighted average, let's say for copper, if this is not copper, I'm gonna cry. Copper 63 is about 62.93 U. And that's about 69.09% of all the copper in the universe. It also exists in the isotope for the most part. Like, let's say this is the only other isotope, copper 65, which is 64.93 AMU. This is about 30.91% of all the copper in the universe. Well, the way you take a weighted average, it's pretty simple. You're going to say, okay, for copper 63, it's 62.93 U, which is about 0.6909 of the total, copper in the universe, plus 64.93 U times 0.3091, and that'll give me my average. Should I run this? I think I ran this calculation somewhere. You should expect, if I were to estimate, you probably should expect something like 63.5 U, maybe something a little bit closer to 62.93, because there's 70% of all copper is copper 63, so the weighted average should lean closer towards 63. But you can run the math and you can see, oh, yes, it should be whatever it is, 63.44, 63. I'm not sure, but I did do this. I just forgot what the answer is. So yeah, that's just a quick little look at atomic averages. Okay, so let's talk about the mole. So remember how we said 100 jelly beans is approximately 5 grams? Well, 100 jelly beans is a pretty convenient thing to count out. So chemists had to think about what's a convenient number of atoms to kind of get the mass of, and then just do all the ratios from there. This is a ratio game. This is what stoichiometry is going to be. It's a ratio game. Ratios are so powerful. They can take us pretty far. So chemists had to think, okay, what's a convenient amount of atoms to say, okay, this is the sort of starting point, my 100 jelly beans. From there, I'm going to take the mass, and from there, I'm going to go beyond 100, right? If that makes sense. Hopefully that line of reasoning makes sense. They decided on, well, what is the number of atoms in 12 grams of carbon 12? 12 grams of carbon 12 is going to have what they define as 1 mole of carbon. So 12 grams of carbon 12 is what we call 1 mole, I'm going to add an E, 1 mole of carbon. So 1 mole is representing a number. 12 grams of carbon 12 will end up actually having about 6.022 times 10 to the 23 atoms. This is the amount of atoms. If I were to, for the most part, if I were to go to the microscopic level, I can't, but if I were to do that and count the amount of atoms in 12 grams of carbon 12, it's going to be 6.022 times 10 to the 23, right? Same way, if I were to take 5 grams of jelly beans and count the amount of jelly beans, I would get 100. That's my sort of special number, 100 from the world of jelly beans, and this is the number for chemistry. Now, it'd be really annoying to say, oh, 5 grams is 100 jelly beans. So I can call that 100 jelly beans, I can give it a special name. I can call it a loonie. So 1 loonie of jelly beans is really 100 jelly beans. I'm giving it a name. Sort of like how we call 12 inches a foot. We call 12 eggs a dozen. We're going to call 6.022 times 10 to the 23 1 mole. Okay? So it turns out, well, you can think, I don't want to go too, I sometimes go on with my videos, I really do try to keep them as short as possible. Based off this definition, well then you can conclude that U, a 1 atomic mass unit, is really 1 gram per 1 mole. It's a gram per mole, right? You can kind of see why that makes sense. 12 grams for 12 atomic mass units, right? Remember, we decided that 12U is equal to 12 carbon. That's essentially the mass of 12 carbon. That's essentially implying that one of these atoms is 12 is 1U, right? So if 1U, wait, that's a little bit, wait, I'm jumping too many hurdles. I think it's just as simple as 12 grams. If you have 12U is the mass of 1 carbon 12. Okay? Well, if I get to 12 grams, so let's say I multiply 12U, right? And I have 12U is just 1 carbon 12. If I get 12 grams, well, we're going to call that 1 mole. Okay? Well, what that implies is then, no, that's also not digestible or accurate. I don't know, does it just make sense? I don't know. Is there a good way to? There definitely is. I just haven't thought of it. I don't want to linger too much on this, but I think you can kind of see if 1 mole is 12 grams of carbon 12. What that means is for every gram per. Oh my goodness! Wait, there's a good way. Oh my goodness! I'm like on the tip of my tongue. There's got to be a way to make this make sense. It's somewhere, it has to do with the 12, 12, 12, right? We said 1U is equal to 1C12. We're saying that 1 mole is equal to 12 grams of 1C12. There's something here. Maybe you don't care that much. So this is just a useful thing to know. Okay? So what that helps us do is calculate molar mass. Okay, so basically with this definition, U equals 1 gram per mole. Well, you can actually do a lot with it because you can calculate, let's say, the molar mass of CaCO3. Molar mass of something is the mass of 1 gram, okay? Or sorry, 1 mole, okay? So if I had 1 mole of CaCO3, what would its mass be? If I have 1 loonie, if you remember, loonie with my definition of 100 jelly beans, let's say I have 1 loonie of not Jelly Belly, but 1 loonie of a knockoff jelly bean brand. What would its mass be? Would it be different? Right? Is that analogy following? Like each jelly bean is made up of different things, and each jelly bean is made up of different things, and we'll have one jelly bean will have a different mass, right? Same thing with molecules. Each molecule will be made up of different things, which will have a different mass. So then 1 mole of each of those different things will be different. Am I tracking? I think that tracks. Hopefully that makes sense. Ask me in the comments if that doesn't make sense. But yeah, that's the story. Carbon, you can check the periodic table for this. Carbon, there's a periodic table at the front. Carbon is 12.01. Oh, this is great. Calcium. Why am I saying carbon? 40.08. How long did I say carbon for? Carbon is 12.01. U. And then oxygen is like 15.99. Oh, 16.00. Fine. Okay. There's probably other decimal places after that. Okay. So, if you want to calculate the molar mass, well, what we got to do, okay, so this is another sort of thing. I think intuitively, if you have 1 mole of oxygen, 1 mole of carbon, and 1 mole of calcium, how much COC3 can you make? You might say 3 moles, or you might say 3 plus 1 plus 1, so no. You might say like, 1, but you have to split that to a third. So 1/3 plus 1 is 4/3, plus 1 is 7/3. So you might say 7/3, I don't know. But hopefully it actually does make, if you think about it a little bit harder, it makes sense that, if you have 1 mole of each, you're gonna get 1 mole of CaCO3. Think about it like this. let's say to make one cookie, you need a dozen eggs and a dozen cups of flour. Not real, but let's just roll with it. Well, if you do have, or no, let's say to make one cookie, you require 1 cup of flour and 1 cup of, or 1 egg and 1 cup of flour. That's probably more reasonable, but still probably not reasonable. If you want to make a dozen cookies, well, therefore you need a dozen eggs and a dozen cups of flour for each cookie, right? So if you want to make CO3, well, you're going to need 1 mole of Ca, 1 mole of C, and then 1 mole of O3, right? That's just how that's going to go. So let's play the number game. Okay, each U is really grams per mole. Now we're going to get into some intro Stoich. Okay, so here's how you can do a little, so this is how stoichiometry is going to move working forward, and just chem math in general. 40.08 grams per mole. So one way you can think about it is, oh, well, I want 1 mole. So it's just, if I get 40.08 grams per mole, right? 40.08 grams for every mole, right? That's what this ratio means. Well, then for 1 mole, I should only have 40.08. It makes sense, but one way you can just mathematically make sure that makes sense is through something called dimensional analysis, where you're looking at the units. I want grams. That's the final result I want. I want grams. Well, if I have moles on the bottom, oh yeah, if I just multiply by moles, makes more sense. If I just multiply by moles, well, that will cancel out the moles in the denominator, and then I'm left with just grams. It's a pretty cool trick. So that's my way to kind of figure it out. So if it's 1 mole, well, then I just get 40.08 grams, okay? But then if I have, 2 moles, I just multiply by 2, and then the moles kind of cancel out, so it's kind of nice. I'm left with grams. It's almost like a way to check your math, and we're gonna do this a lot more. So 1 mole of this, will give me 12.01 grams, and then 16.0. Well, I need 3 of these, so I'm gonna multiply by 3. So now O3 is really 48.00 grams per mole, and I want 1 mole of O3. So that would give me 48.00. And I believe you could have done, I believe, just through a reckless little thought, you could have just said, 1 oxygen, 1 mole of oxygen is, yes, you could have done this. So another way, you probably thought of is, 1 oxygen is 16 grams per mole, so 1 mole of just oxygen is 16. Well, to make 1 mole of O3, I would need 3 moles of oxygen. That seemed reasonable, right? So, 16 plus 16 plus 16, that's gonna be 48, right? Hopefully that makes sense. To make 1 mole of oxygen, I would need 1 mole here of 1 oxygen, 1 mole of another oxygen, 1 mole of another, right? If I was making scrambled, so let's say to make 1 dish of scrambled eggs, you need 3 eggs. And if you want to make a dozen scrambled eggs dishes, well, you need 1 dozen eggs for 1 egg, a dozen eggs for another dozen, so that'd be 3 dozens. Hopefully that makes sense. You don't have to overthink this, but if you do the mental gymnastics, you should feel really solid about this. Okay, so I can just add this up. So 40, let me get my calculator. I'm doing this problem for the first time. And that way we can find the molar mass. 40.08 plus 12.01 plus 48. So that should be 100.9. Let me check my answer. So 100 grams, okay? Where is it? 3.4. 4 we're on, right? I'm really tired today. I'm sorry about that. I got it wrong. Why did I get it wrong? Did I get it wrong? No, I got it right. 100.09. Oh, I forgot a 0. That's why. Okay, 100.09 grams. So 1 mole of CaCO3 has 100.09 grams. That's an awesome thing to know. I'm going to show you why it's an awesome thing to know. Because, hey, let's say we have to calculate the mass of 4.86 moles of CaCO3. Oh, well, hey, look at this. I'm going to do some work with ratios. I have 4.86 moles. Okay? My end goal is I want something in grams. Let me kind of erase some of this stuff. We don't really need too much since we kind of did the problem. Okay? I want something in grams. So I know the ratio I have to multiply by, I want grams on top and moles on bottom. Does that make sense? I need to get rid of this mole that's going to be on top when I multiply by the fraction. So I'm going to have a mole in the denominator. So I need some sort of grams per mole ratio. If I started with grams and wanted moles, do you see how I have to flip that? Because now I have grams on top and I would need grams on the bottom. So my ratio would then have to be moles per gram. But since we have moles on top and want to get rid of it, we're going to do grams per mole. It'll feel intuitive when you practice more. It's just one of those things where the more you do it, it's just going to make sense. So not make sense, but yeah, I think it will make sense the more you do it. Okay. Well, hey, I just found out that in 1 mole, it's going to be 100.09 grams. Okay, and honestly, this, so yeah, 100.09 grams. When I multiply this out, it's just 4.86 times 100.09, so multiply that by 4.86, I get 486.4374. Sig figs will do soon, like sig figs will matter eventually. Significant figures, how many decimal places I want. So yeah, there you go. You might have thought this is kind of doing too much, right? Because we just know, oh, if 1 mole has 100.09 and we want to find 4.86 moles of this, oh, I just multiply the two numbers. That would make sense. But let's say we lived in a universe where molar mass meant finding the mass of 2 moles of CaCO3, which is called, I believe, calcite, by the way, calcium carbonate, which is just shortened to calcite. So like, let's say, oh, in some alternate universe, finding molar mass means finding the mass of 2 moles. Well, then this number would therefore represent, well, obviously this would have been scaled up by 2, but then that would mean dividing by 2 on the bottom, because now the ratio is 200.09 grams for every 2 moles, because this number tells me in this alternate universe what is the mass of 2 moles. So the ratio is 200 to 2. Does that make sense? Hopefully that tracks. And you should get the same answer. But it's just 100 to 1, plain and simple. Okay, nice. Now the last thing this question is asking, I'm gonna just check the time just to make sure I'm not, 23 minutes, it's a little long, but whatever. What is a CO3 present? What is a carbonate present? This is pretty simple, because if you have to make 4.86 moles of this dish calcite, I would have needed 4.86 moles of CO3. Okay, 4.86 moles of CO3. Well, I just got to add these two numbers. That would give me the molar mass of CO3. I just don't need I'm at the waiter is asking for the nutrition of just this part of the dish. Analogies, I'm trying. You have your chicken salad. The total calorie count of the chicken, of the whole dish. Now I'm just wanting to know what is the calorie count of just the chicken. Hopefully that analogy tracks. I like analogies. Maybe you don't, but that's just how I operate. So I just got to get rid of the carbon, right? Yeah. calcium, oh my goodness, 12.01 plus 48, 60.01, right? 60.01 grams is in 1 mole of carbonate. Oh, I just got to multiply that by 4.86 now, right? Because now I do the same thing, 4.86 moles, and then I put the 60 here, grams per mole. Should give me 291, about 292 grams. You know, sig figs, it'll be like 291.6486. But there you go. Last point I'm going to touch on quickly, learning to solve problems. If you're in college, you've probably been a problem solver for at least 5 to 6, 7 years, right? Because that's really high school and middle school. That's, I think, where you really are solving problems. In elementary school as well, but you don't think through it as much, maybe. I don't know. You've been a problem solver your entire life. A little bit useless to read a passage on it, but I did read it, and I actually thought it had some good points. Solving problems, so to solve a problem, you're asked a problem, okay? Let's say you're physics is my forte. I'm just gonna go to physics. Let's say you're asked to solve the problem. Oh, I drop a pen. It's gonna fall 5 meters. Given that gravitational field strength is 9.8, what is the final speed when it hits the bottom, right? Okay. There is a process to solving this physics problem. Here's the general process. Know what you're given. So I'm given acceleration due to gravity. I'm given the distance that it falls. I'm essentially given the initial speed. I know it's 0, and I want to find the final speed. Okay? So 3 givens, 1 unknown. The next part of the process is pick an equation that has all of your knowns and 1 unknown, right? Notice how in this problem, I wasn't told anything about time. And that would mean 2 unknowns, final speed and time, if I pick an equation with both those things. So I know my equation should not have time. It should have final speed, shouldn't have time, right? So I would go through my equation sheet, or my head with equations, and be like, okay, v squared equals v initial squared plus 2a height, 2ad. Oh, great, that has my 3 knowns, initial speed, distance, gravity, or acceleration, and that has my unknown, the final speed. And then I would plug it into my calculator, do the algebra, and solve. Or do the algebra, plug in the calculator, solve. Okay, that's a process. Okay? But the problem with that process is that only will work for constant acceleration problems. What if I introduce drag, air drag? Now, my process comes to a quick halt, because if I only knew that process, then I would have no idea, well, what does the air drag do? Okay, it creates a force. I gotta check the time. I don't wanna make sure I'm going over. Okay, I'll give myself 2 minutes to see if I can do this tangent. Air drag. That introduces a force that opposes the force of gravity. What are forces? Oh, forces are these things that cause acceleration by Newton's second law. F net equals ma, right? F net equals ma. Great. Now, F net equals ma, I can look at all the forces and figure out the acceleration. Drag force is known to be proportional to speed. So my net force equation, I'm building this out. mg is my weight force. Subtract by bv, which is my air resistance force. B being a constant, and it's proportional to v. mg minus bv equals m acceleration. What is acceleration? Acceleration is the rate at which velocity changes. So mg minus bv equals m dv dt. That's the time derivative of velocity. That's what acceleration is. Okay? Great, I have this differential equation. How do I solve differential equations? It's a linear differential equation. It's first order linear. I have the Leibniz method. Leibniz. I think it's nits. Leibniz method. Leibniz method. Doing a product rule thing. I can make it separable and do it that way. And then I come to an answer. That train of thought required a lot more understanding about physics than the first. Because the first, no acceleration, I follow a streamlined process. I don't have to think. I just do what I'm told. I'm like a robot almost. But the second, you need a little bit more understanding. And then you can make that into a process. But to get there, you needed a little bit of understanding. And if you were shown the air drag problem on your own first, you can't solve it if you don't understand the parts. That's where good problem solving skills matters. Understanding the problem and understanding what's causing it. All right? Let's say I have to drive from my house to the library. My friend maybe takes me there for the first time. And I'm stealing this analogy from the book. But if I watch my friend drive me, I could probably be like, okay, take a left here, take another left, okay, take a right, go straight for a little bit, and then take a left. Boom. Perfect. Well, how do you get back home? You're going to do that same thing again? Probably not. You're not going to do the same thing. If you understand how directions work, it's pretty clear you're going to go essentially the opposite sets backwards. So you're going to kind of do that whole list backwards and then flip the orders because, oh, that's how direction works. You understand that if I go left, in order to get back to where I was, I need to go right. Simple concept, but if you don't understand it, then you can't get back home. Likewise, you can't just use that direction anywhere. If you want to go to the grocery store, right? Let's say this is your home. Let's say your library is here. Okay? And let's say the grocery store is right here. Okay? Library, grocery store. Make my pictures look nice. If you memorize this little step to get to the library, if you don't even understand the basic thought that, oh, this is to the right of me, it's no longer to the left of me, taking a bunch of lefts is not ever going to get me there, you're doomed, right? Like, you can't get there because you just lack that basic understanding of the map and location. Your goal with chemistry, your goal with physics, your goal with law or history or any of your problems in life, understand what you're looking at, understand the space of the problem, know the map of where you are and where the solution to your problem is, and you gotta then figure out how to get there, right? If I give you an air drag problem to an AP Physics 1 or an honors physics student where there's no calculus, okay? If they do the kinematics, no constant acceleration approach, like, they don't even understand that the answer is to the right and they're just going left. Now, a good student would be like, wait, I understand how forces work. My constant acceleration approach won't work, right? They'll at least know, oh, I shouldn't go this way. I'm going to get to somewhere I don't want to be. I got to go this way. And then that same student, if they're curious enough, they're going to figure out what are the tools to get me to go right. Understanding while you solve problems is really important. So you're not just doing a procedure without repeat. That's my spiel on how to be a good problem solver. It's hard sometimes, takes more time, but you know what? I think it's going to be worth it in the end.